to control nature. Although CO2 is not soluble in water, we can force CO2 to be soluble in water. So how can we get more CO2 or get CO2 to dissolve in water? Yeah, one way is part C, raising the pressure. Now, can we get CO2 to dissolve in the water by using hot water or cold water? Cold water. Hot water. Okay, so you may have done this before. You have a bottle of soda, and you can see through the bottle. So here's your bottle of soda. Now you often see bubbles. You often see bubbles in a bottle of soda. Okay, so the bubbles are the CO2. So if you leave this at room temperature, you see more bubbles or less bubbles? I'm depending on you guys to, because I don't drink soda anymore.
It's like when you throw it in the freezer, it drops the temperature.
Okay, so I prefer, well, let's do this. So you have a brand new bottle of soda, and then you twist open the cap, and what do you observe? Yeah, so what's that noise coming from? And why is it coming? Is the CO2 going out of the bottle or in the bottle? Out. Why is it going out of the bottle? Yes, in other words, are you saying that before the bottle is open, there is a high pressure of CO2 inside the bottle?
Yes.
Yes. So note that when you open the bottle, you're equalizing the pressure. Okay, so the high pressure in here is then becoming the atmospheric pressure. And you're seeing that sound that you hear is actually the CO2 coming out of solution. So if you have a cold bottle, now you have this open cold bottle of soda. There's these bubbles you've seen come out. As you leave it, as it warms up to room temperature, you're seeing more bubbles or less bubbles. Or another way to ask the question is you have an open bottle of soda, it was cold initially, you forget to cap it. Does it go flat or is it still as bubbly and carbonated as it was before? And it goes flat, so what does that tell you?
Cool down the water.
Yeah, so what does this tell you about A or B? So can you get CO2 dissolved in water by heating up the water or by cooling down the water? So you can get it to dissolve by, who says A, by heating up the water? Who says B, by cooling down the water? Yes, you're right. So you can actually get more CO2 dissolved by cooling down the water. In other words, CO2 is more soluble in cold water than it is in hot water. Now note that that's the opposite of solids. So solids tend to be more soluble in hot water than cold water, where the gases is the other way around. Okay, so for this question here, it's actually B and C. You can either lower the temperature of the solvent, or you can raise the pressure of the solute onto the solvent. Okay, and here's something too. Have you heard of this gadget called fizz keepers? Okay, fizz keepers. So you have your bottle of soda, and what it is, you screw on this thing here, and there's a little pump. So it says, okay, so what you can do is you can pump more or something into your soda to recarbonate it. Okay, so that's what fizz keepers they sell. I think yeah, so here's the website, fizzkeeper.org. And then this guy, Steve Spangler, he was I'm not sure if he's still, he was a reporter for Denver.
Can we break again?
Science experiment. This one here. Oh yeah, you can buy it at Amazon.com.
How much are they?
They're like $5 or $10. So is it going to work? So you're pumping this thing up. You're pumping it to increase the pressure inside the bottle. So is that gonna recarbonate or keep your soda from going flat? Yeah, so all you, like Lewis said, you're only like adding air. There's like, depending on, there's only 200 parts per million CO2 in air, which isn't very much. That's way less than 1%. So by pumping air in there, that's not going to make your soda recarbonate. It's not going to help. It's not going to help the soda keep going flat.
Well, it won't keep it from going flat, but even though you're creating a greater pressure on the surface.
Yeah. So what's happening is you're actually pumping air, oxygen, and nitrogen into the soda, but not. In air, there's less than 1% CO2, so a little bit of CO2 is going in there, but hardly anything. If you blow on the tip of it. Let's see, according to, let's see, I know we exhale CO2, but that's also with air too. So it's not, there's more CO2 in your exhale breath than so I guess are you saying that by exhaling we're contributing to global warming by exhaling we could all stop the Earth from
Stop breathing.
hold our breath.
So then you gotta breathe.
Yes. So really, if there's a way to add CO2. So really, the way to keep your soda carbonated would be to close the bottle and
Put it in the refrigerator.
yeah, keep it cold. Put it in the fridge. Okay. Okay, so here's another property. So these are called colligative properties. Now, these colligative properties include freezing point compression, boiling point elevation, osmotic pressure, and vapor pressure lowering. So there are quite a few applications of these. So, for example, for freezing point depression, you can make ice cream using salt, and you can do that in the lab too. Okay, so you do that, I think either next Thursday, 1 week from today, or the following Tuesday. An application of boiling point elevation is why you use antifreeze in your car cooling system, okay, to keep your car engine at a normal operating temperature. If you ever had your car boiled over, then you know the importance of having antifreeze is actually something besides having your cooling system. So osmotic pressure, you can use that to keep your veggies crisp, or you can use it to lose weight. All that's not recommended to use osmosis. And for vapor pressure lowering, that's the fourth colligative property. That you can use that to keep solvents from evaporating. In other words, you can make a volatile liquid less volatile. Okay, so here are some equations, and we'll look at these equations in more detail. So let's take a look at it qualitatively first before doing some calculations. So the freezing point of a saltwater solution, is it higher, the same, or lower than the freezing point of pure water? Okay, so we don't live in a place where it snows, but what's the reason for putting salt on ice on roads? So that's so that melts the snow, which means what's it doing to the freezing point or melting point of water? It's lowering the freezing point of the water. Okay, so by adding a solute to water, that's going to lower the freezing point. That's why it's called freezing point compression. It compresses the freezing point. Question 2, the boiling point of a salt water solution, is it higher, the same, or lower than the boiling point of pure water? Yeah, higher. So we talked about that when we cooking spaghetti or beef. Okay, here's part C. You ate way too much during the holidays, and your exercise program just isn't working as fast as you want it to work. Someone tells you to soak in a concentrated salt water solution for 1 hour. Will you gain weight, maintain your weight, or lose weight?
Lose weight. Lose weight.
Has anyone ever been to the Great Salt Lake in Utah? No.
Yes.
Did you go swimming there?
No.
Very salty.
It's salty in the ocean.
Yeah, it's easy to float. It's easy to float because it's so salty. But there's no, yeah, what else happens?
It takes the water.
Yeah, so will you gain weight or maintain your weight or lose weight if you soak yourself in a salt water solution for an hour? And you're going to lose weight because of osmosis. So what's happening is that in osmosis,
You shouldn't want to lose weight that way.
okay, so here's your cell. This is your cell. There's about 0.9% salt in your cell. That's the physiological concentration of salt. So if you're soaking in, say, it's like a 5% salt solution, now is the water, so there's also water here. Is water going to go from the outside to the inside of the cell, or from the inside to the outside of the cell? Yeah, so through osmosis, it goes from the inside to the outside. So it goes from the high water concentration to the low water concentration. That's how osmosis goes. So osmosis is defined as the movement of water through a semi-permeable membrane due to a difference in the concentration. Yeah, so this is not